Hi, today I'm going to talk about random stuff, mostly science and business and all that stuff. I've studied probably 15,000 or more hours in the past 15 years, and I really like knowledge. What I really like is finding common patterns among seemingly unrelated things, that's pretty cool. How, like, a common thread woven among the different seemingly unrelated subjects. Walmart Walmart, I think, is pretty cool. I read Sam Walton's book, Made in America, and he went through a lot of rules and different things. And toward the end of it, he said, talking about, like, those kinds of rules, he said, break all the rules, like all the rules that he told about. And I think that concept is kind of interesting because Steve Jobs, at the end of his commencement speech at one of the universities, he said, stay hungry and stay foolish. So being unique is important, not necessarily just for uniqueness sake, but each person, in my opinion, has a unique set of values and ways of doing things. And that can contribute to, helping people. That can contribute to helping people. And I think that's, one of the main reasons we're here on Earth is to help people. And so anyway, I thought that was pretty cool. So another book that's kind of interesting is The 7 Habits of Highly Effective People by Stephen Covey. I've read that book, and I've read another version by his son. That version by one of his sons, I've read. There was a period of 480 days where I read at least some part of each chapter, or one, like, just say chapter 1. I read some part of that every day for 40 days in a row. Chapter 2, some part of that every day, 4 days in a row. Chapter 3, 4, and so on, for 12 chapters, and did that total of 480 days in a row. And it was interesting. My goal was to make a habit of the 7 habits. And so, yeah, that was pretty cool. Another book that's interesting is a book called Poor Charlie's Almanac by Charlie Munger, Warren Buffett's vice president at Berkshire Hathaway. He lived to be 99 years old, and he is really wise. What he talks about is creating what he calls a lattice work of mental models. These are things that they're the big ideas in the different subjects. Like he was pointing out, there's not enough time to master every subject. So what he did was he'd look at key ideas from economics, psychology, finance, etc., and figure out he would figure out the key ideas, and he would use those to filter out decisions. He would use those to make decisions with. In economics, for example, is opportunity cost. That says, if I'm doing one thing, what's the next best thing that's costing me the opportunity to do? Just say if there's a CD and I don't know if people buy CDs anymore, but if there's a CD and a book, and somebody said, here's $20, only use it to buy the CD or this book, because each of them was $20. And if you bought the CD, it would cost you the opportunity of buying the book. Or if you bought the book, it would cost the opportunity of buying the CD. So that's opportunity cost in economics. That's one of the filters. I actually had a vending machine one time, and it was financially profitable a little bit, but I figured in the opportunity cost was the time I was spending on it. It cost me the opportunity of working somewhere else and making a certain amount of money per hour or whatever. And so it turned out to be not economically profitable, so I sold it. And then there's some other concepts? Compound interest. If somebody, all things equal, this is not investing advice, but all things equal, if you do the math on it, if there was $100 a month at 12% interest for just age 25 to 65, if somebody put in $100 a month at 12% interest from age 25 to 65, at 12% interest, compound interest, The amount put in would have been, I think it was roughly $60,000, but the total with the interest on top of that would be $1,176,000. So that's the concept of compound interest. Another one of the mental models. Another mental model is in psychology. It's confirmation bias. Everybody has this. Everybody does it, whether they realize it or not. It's looking for things that support what people believe and ignoring things that go against that. Somebody wanted to say broccoli was unhealthy. They could look up online, why is broccoli unhealthy? And people would probably find places telling about that. And if there was places that said it's healthy, they might ignore that. But if somebody looked up why is broccoli healthy, then they'd probably see that and ignore the places that was, if it was saying it was unhealthy. And so, from as far as I'm aware, it looks like it is really healthy though. So that's the concept of confirmation bias. It's looking for stuff that confirms what a person believes and ignoring other stuff that doesn't align with that. So that's another mental model Charlie Munger has used. And he has, I think, before he passed away, I think he had, well, at one point at least, he had over $2 billion in financial net worth. And he's donated a lot of money to different places. Then there's, well, yeah, that's some of the mental models. So another concept that's really important, in one that I've observed in economics and calculus and a lot of stuff in general, is the idea of, like in calculus, when you say, if you're doing multivariable calculus, you hold all the variables equal except one. You change only that one and see what the slope is. You change only that one and see what the derivative is based on the change in that one. And so if you have x, y, z as the input to functions, and it would hold y and z as constants, but you would change x, it would say, what's the derivative of f of x with respect to an infinitely small change in x, or as delta x approaches 0 or h approaches 0, whatever. So where you have, the first principles formula in calculus, which is f of x plus h minus f of x divided by h, or you have another way to phrase it, in case you've heard of this, is f of x plus delta x minus f of x divided by delta x. But if you actually look at that, or anyway, that's it's in economics, it's where you hold all variables equal. Let's just say like Coca-Cola. If somebody was trying to figure out, if you ran the Coca-Cola company and you were like, Coca-Cola, we make this much profit. If we make a slight change, or if there's a slight increase, just say by $1 per ton of corn syrup or whatever goes in Coca-Cola, if there's a $1 per ton increase in that, then how's that going to affect the price of Coca-Cola, a can of Coca-Cola? And because there's so many ingredients and so many variables that could play into the price and cost of it, that it would get too confusing if you try to figure them all at once. So what you do is say, if everything else is equal, all things equal, and we only accept this one thing, and we only change this one thing, how would the end result change? And that's the same type of concept that's used somewhat in multivariable calculus. So that's a useful mental model for figuring things out. Have a complex subject, have a complex thing, and just isolate one thing at a time. Say, if I make a change in here, how does it affect the end result? And then once you do that, then just start over and change a different variable and say, if I make a change in here, how does that affect the end result? And that's really useful for lots of stuff, problem solving and figuring things out and breaking complex problems into simpler ones. So now with calculus, you may have heard of first principles, and that's where you have, like I was mentioning earlier, you have the first principles formula, which is f of x plus h minus f of x, which is f of x plus h minus f of x divided by h. And h is the change in x. So if you notice, though, if you remember the slope of a line from a Cartesian coordinate plane of 2 dimensions, a xy graph, the slope of a straight line, it's change in y over change in x, or another way to phrase it, delta y over delta x, or it's called the slope or the gradient, or it's a lot of words meaning the same thing basically. So in calculus, you say change in y over change in x, but if you plot on the y-axis, instead of saying y, say f of x, and on the x-axis just put x. So you have f of x, and where x is the input. So you take x here, or whatever you put in here, that goes into the function. Basically replace this x with whatever this x is on the x-axis. So just say you put 3 in here. So 3 goes in place of x in f of x. And so it's say f of 3. And then you say, where does that go in the vertical line? Or where does that go according to the y-axis? So you'd say you have f of x here. Now at the bottom where you have x, you can say if I add some to it, that would be this original x plus whatever I add to it. And just call whatever you add to it like a change in x. Because this is x, and if you change it some, then you have this x plus a change in x. And that would be, change in means, or the word delta is used for change in mathematics. So you could say x plus delta x. So what you could do then is say the change in y would be the f of x. Okay, so the y2, y2 minus y1 over x2 minus x1 in the slope formula for a straight line, you could say y2, or I'll say y is equivalent to f of x. So y2 would be equivalent to f of x plus h, because remember x plus h is what you added to x, because you have x and then you have whatever amount x is plus h. So you have x by itself, and then you have whatever the second part is the value of x plus h. So this part is for the second dot on the line, I guess you say, of a 2D graph, a 2D xy graph. So you have x plus h is the x2, I guess you'd say, on the y2 minus y1 over x2 minus x1. So you have the x2 is equivalent to x plus delta x, or x plus h, or else x plus delta x, whatever you want to call it. Delta x equals h, so they're the same thing. So x plus delta x goes in place of x on this f of x function, and so that would be y2. X plus delta x is x2, so now you have y2 and x2, and then go to the original ones, which is x, that's the x part, or x1, and you have f of x, which is y1. So now you can take the y2, which was f of x plus delta x, and subtract from it f of x. That's like saying y2 minus y1. And then divide that by, remember the x2 minus x1. So x2 was x plus delta x. And now if you minus x1, which was x, you have x plus delta x minus x. So you have, if you do the math on it, and that's on the bottom of the fraction, you have x plus delta x minus x. So you can rearrange it and say delta x plus x minus x. And x minus x is 0. So all you have is delta x left on the bottom. And so now you can say f of x plus delta x minus f of x divided by delta x. And there's the first principles formula in calculus. And you can bring that delta x, make it approach 0. Like once you work out the calculations on this stuff, you can make delta x approach 0, bring it infinitely closer to 0, and that'll give you the derivative, or in other words, the slope at that specific point on the xy graph. So you can figure a secant line you could say if this is a slope and it's crooked, if this is a slope and it's crooked, you make a straight line from here to here, and you could figure out what's the slope of that straight line, and that'll give you the average slope of this curved line from here to here. But if you want to get more accurate, you could say like from right here to right here, and that would give you average slope over here if you made a straight line from here to here. And you could keep doing that you say what's the slope from right here to here, and you could make a straight line and get the average slope from here to here, and it would be a bit more precise. And you keep making the secant line smaller and smaller and smaller to get exactly at that point and say what's the slope of the line at that point. And that's what the derivative is. That's what the derivative of f of x is. So that's first principles in calculus, and you can figure out derivatives from that. So another thing that's useful is electricity. You have V equals IR, which is Ohm's law in electricity, and it says voltage equals intensity of current times resistance. Voltage is in volts. The intensity of current is in amps, and the resistance is in ohms. So the intensity of current is amps, but if you break down amps consist of coulombs per second. 1 amp is 1 coulomb per second, or rather 1 amp is 1 coulomb in 1 second. So if you have 1 coulomb and 1 coulomb, if you break that down, it's equal to about 6 times 10 to the 18th electrons, or 6 with 18 zeros after it electrons. And so 1 coulomb is that many electrons. The 6 with 18 zeros after it, it's that many electrons. And if that many go by in 1 second, that's called an amp or an ampere. An amp or an ampere. So that's the intensity of current. So V equals IR, the I, intensity of current, is how many electrons are going by, or how many coulombs of electrons. Remember, a coulomb is that 6 with 18 zeros after it, that many electrons. So how many groups of those are going by per second? So 1 amp is equivalent to that many electrons going by, 6 times 10 to the 18th electrons going by in 1 second. So V equals IR, the analogy to this is a water hose. You put your thumb over a water hose, and the pressure is like the voltage. The amps are like the drops per second going by of water, and the thumb over the water hose is like the resistance. If you increase resistance by putting your thumb over the water hose more, then it increases the pressure, which is equivalent to the voltage. So the same thing in a wire, if you increase the resistance, all things equal, the voltage increases. If all things are held equal, the voltage increases. But it's still the same number of electrons that are going by per second. So that's like the amps, is how many electrons, or how many coulombs of electrons are going by per second. So that's more useful stuff too. Also some more helpful advice, or also some more helpful things are ESP32 circuit board. I've used Arduino and that can use MicroPython. MicroPython is easy compared to C++. C++ not super complicated, but it's a lot less code to write. Like I can literally turn something on and off like a motor or whatever in 2 lines of code with the ESP32 using MicroPython. If I were to use Arduino, the Arduino IDE with ESP32, or with the ESP32 or with an Arduino board, it would be a lot more lines of code than that. But the trade-off is MicroPython is a lot slower than C++ that's used in Arduino. So if it's time critical stuff, then the C++ would be better, depending on how much time criticality it is. And another valuable lesson I've learned, which I wasted probably about 17, 18 hours, or maybe like 18 hours on, was I was trying to get a motor working for a robot lawnmower, and I put the wrong amperage motor controller on it. I didn't know that the motors would take so much amps, and I put a L298N that only handles, I think, is a maximum 2 amps, and it's supposed to, well, I'd previously made a plywood car that I controlled with the GUI that I built in Python, and made it also controlled by Bluetooth, and I made it controlled by just, what else? Something else. Oh, where I could turn it on and off on my website over the internet, and just different things like that. Oh, and I made it, controlled by computer vision as well. I could put a picture of a stoplight in front of it, and it would stop and remove it, and it would go. Or I could put pictures of different things in front of it, and it would behave different according to what I put in front of it, however I programmed it to behave based on picture. And actually have some videos of that on my YouTube channel, that kind of stuff. So anyway, the L298N, it's convenient for things that don't require a lot of amps, but this did, and I didn't realize how many it required. And I burned up a couple of those, I guess it was the circuits inside those L298N boards. And I think I burned up 1 or 2 of the ESP32 boards, which they're about $5 to $7 a piece. $5, $6, $7, somewhere in there. So they're relatively cheap. But anyway, I got the mower working. Excuse me. Anyway, I got the mower working, and I can mow the lawn with my thumb using a joystick now. I have a video of that too. I haven't got it to turn yet, but it's, at least it goes forward and backwards. It does have a little bit of offset on the motor. One of the motors is, I guess, not perfectly aligned calibration with the other, so it slightly turns by itself, and like in one direction. So I can push forward, and it'll go mostly forward with a slight turn, and then when I pull back, it mows a little bit of a different spot of grass, and I can go back and forth and mow different sections of grass. But anyway, I probably I used a different motor controller. I'll grab it. I used this motor controller, and that worked. So that's I forgot what it's called. I don't see the model on it. It's a 40, I think it's a 43 amp. It's a 43 amp motor controller, and it's it works really good. So I think if there's any more stuff, my air conditioner broke, and I watched a video about it. They didn't describe why it worked, rather, when they fixed it. Like the 5 or 6 volt control board in it or whatever. I figured it out, and it's a lot like those circuit boards, like Arduino type things. At least in this air conditioner it was. And so I actually pulled the control board out and replaced it with the ESP32, and now I can wirelessly control the air conditioner. I can control it from my computer by clicking a button on a GUI I made, or I can control it over the internet from my website, or I can set a temperature limit on it and use one of my cheap temperature sensors and make it automatically turn it on and off based on temperature. Or I can set a timer on it, which I have it like that now, so that whenever it's connected, the air conditioner will turn on for, just say, like 15 minutes or 30 minutes or whatever, and then turn off for like an hour and a half. Where it'll turn on for like 15 minutes and turn off for an hour and a half or something like that. And so anyway, that works good. And what else? Yeah. Oh, anyway, The 7 Habits is a really good book. It's really useful, and I've read quite a bit of books, but if you calculate all the books that I've read, and if you converted all the educational videos I've watched, like YouTube and Udemy and stuff like that, if you convert all those into transcripts, and those transcripts into equivalent number of words of 250-page books, and all the articles I read and all that, if you convert everything into number of words and divide that by how many words are an average, like just say about 250 page book, I estimated that its equivalent for the educational stuff that I consumed is approximately, I don't know, 3,000 books equivalency, something like that. So, yeah, and one thing I've read about like different inventors and people that are best in the world at certain things and so on. One thing I've noticed is extreme amounts of reading, like thousands of books, and like, you know, Nikola Tesla, for example. One of the main reasons we have, electricity right now that's not ridiculously expensive. It may be pretty expensive, but it would be way more if it wasn't for stuff he made. So basically, he somewhat invented three-phase electric current, if I remember correctly, if I understood it right. Three-phase alternating current. So yeah, I'm glad he did that. Very thankful. And like I listened to his autobiography. I listened to his autobiography audiobook, and he was saying that there was a book that he read. Then after he read it, that he realized that was one of a series of 100 books in that category, and he didn't want to read them, but because of his, I guess you'd say, he read a lot and his somewhat obsession with completing things, he read the other 99 books. And so, yeah, that's a lot of, reading for a series that you don't really like, I guess. I think he said he didn't really care about it a whole lot. But anyway, he read a lot. And Elon, I believe he said that he's read thousands and thousands of books. He read the encyclopedia twice when he was 12 years old, around that age. And he pointed out a lesson that he learned was that by reading the encyclopedia, you learn stuff that exists that you didn't know existed before. That's pretty, cool. And people like Bill Gates, he's read like enormous amounts of books, and like, I know there's some controversy over, different ones and stuff, but however you look at it, we have computers. A lot of it is thanks to, him and Microsoft. And the technology wouldn't be near as advanced without them. So thankful for that. I don't know about the, other stuff, controversy, whatever stuff. But anyway, I'm just, thankful that we have computers. And if we, don't like them, we can, sell them. We don't have to use them. But I like them. So, and Steve Jobs, and just think of inventions, how good they are for the world in general. Not every invention, obviously, but in general, inventions have made people's lives so much easier. Imagine going to the grocery store without a vehicle, just walking there. Thankful for inventions and, air conditioners. At least here, it gets to sometimes around 100 degrees in the summer, and it's humid. And so I'm very thankful for the invention of the air conditioner, whoever made that. Whether they got rich off of it or not, whatever, I'm still thankful that they invented it. If you do the math on it, like, if somebody makes, just say, makes an invention that helps people so much they're willing to pay $10 for it, and just in the United States, for example, just hypothetically, in the United States, or just in the United States, for example, there's about roughly 350 million people. So if 1 out of 100 people buys that for $10, then that's $35 million. So I wouldn't be mad at somebody for making a useful invention. I mean, it depends on the person. There's other stuff to it and so on. But in general, all things equal, I wouldn't be mad at somebody who made a useful invention such that people would be willing to pay $10 to them, and if they sold 3.5 million of them at $10 a piece and made $35 million, I'd be happy for them. Be like, hey, this stuff helped people a lot, so thank you. Here's my $10. Thanks for helping me so much. So, yeah, it's just, it's, yeah. Understand other views too, that, you know, it seems like they have a lot of power and stuff or whatever, but it's, whatever the deal is, I don't know all this stuff about it necessarily, but I know that it's just, the math. If you help somebody so much, they're willing to pay you $10 for it. If you help 35 million people, or if you help 3.5 million people that much, all things equal, then you get $35 million. Of course, you subtract taxes, and if you tithe, you subtract 10% of the income also, and blah, 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 so on. But I think inventions, like physical wise, have helped people more than anything. Just think of, you're watching this on probably a cell phone or a computer or a television, and probably an air conditioner in an air conditioned room with lights, and it's just inventions I think are really useful and helpful for people. So, what else? Yeah, I'm thinking. Excuse me. And technology doesn't automatically move forward. It moves forward when people push it. So I think wise technology advancements are important. It's good to make sure they're not done wrong, but that they're done right. So a lot of stuff is amoral. Like somebody was pointing out, Dave Ramsey, I believe, that teaches like finance principles and stuff, teaches biblical finance principles and different things. He was pointing out a brick could be used to throw through a window and harm stuff that way, like break a window, or it could be used to help build an orphanage. In other words, the brick in and of itself is not good or bad. It's just there. It's amoral is the term used for it, but it's how the person uses it. Understand that concept could play into other things and how it could play into it, and but I mean in general stuff like some technology, how it's useful, like computers and cars and cell phones and stuff like that, and air conditioners. I don't know many people that would disagree that air conditioners are useful, but anyway, that's pretty cool. I like inventions, and see what else. What else is useful that would help people? From what I've observed, billionaires or people that are best in the world at certain things or whatever, in general, the common thing they have is focus, like hyper focus on one thing. And like Jeff Bezos was pointing out, have the goal, but be willing, or basically be intensely focused on the goal, but be flexible in how you get there. So, in other words, for example, if somebody is planning on building, I don't know, a safer car, and they wanted to do a certain way, but if there was certain laws of physics that they didn't think of before, or certain regulations or stuff like that, safety regulations and stuff, it's all right to adjust the thinking and the planning toward the laws of physics, because you can't really break the laws of physics. So it's good to adjust toward those and so on, and follow the regulations and so on, follow important regulations and so on, and get toward the goal. And so be focused on the goal, but be flexible in the path to get there. Be flexible in the ways to get there. In other words, but like Gandhi was pointing out, it's just as important how you get there as it is that you get there, somewhat. Like, for example, in other words, do stuff right all the time. In other words, doing things right, treat people good, and so on. Yeah, and I understand that, sometimes people get, if they don't sleep much, like different people, like that if they don't sleep much, then they'll, sometimes people are gripey, stuff like that, and it's general good to try to sleep right. I know it's, sometimes hard to do, but anyway, yeah, what else? Oh, something I think's really cool is light, and a bunch of different stuff, but like light, for example, when you're watching this, you're seeing light hit my skin, bounce off of it, and go into the receptors or whatever you call it inside the camera, and they're picking up the different levels of red, green, and blue, or they're picking up different light, and it's storing stuff with electrons inside memory, and it's going to be transferred to YouTube servers, and the servers are basically computers in a warehouse, and so those electrons through invisible light, which is radio waves is invisible light, one example of it. There's radio waves, X-rays, gamma rays, etc. But the radio waves, and there's microwaves also, but the radio waves are gonna do stuff to make electrons move in certain places or whatever in Google's computers, so that they're stored in a certain pattern, and they make stuff either on or off, and that's what binary computer language is, or machine code is called. You've heard of ones and zeros. That just means it's the thing on or off. So once it goes into the computer, it's stored, and then when you watch the video, you're connecting to that computer, and you're watching the video that's on that computer. So that's kind of how the internet works. So yeah, that's pretty cool. And then you have just say if you have a 4K TV that's approximately 8 million pixels that's making up the picture, and each pixel consists of 3 lights in general: a red, green, and blue light, because those are primary colors of lights, and you can mix those to make any color in the visible spectrum. And so there's 256 different levels of brightness for the red, green, and blue. And so you have the red, green, and blue lights. And in programming, you can adjust each one of those lights to 256 different levels of brightness, ranging from 0 to 255, because there's 256 numbers. 0 is off, 255 is the brightest. So you mix those in different proportions, and you have equivalent to 256 cubed, which is approximately 16 million, about 16 million different colors that can be made with those 3 lights, with the 256 different options. The reason it's 256 is because a bit is on or off, the ones and zeros. So you can have something's on or off. That's 2 options. So with these 2 options, if you add another bit, you can have, the original on and off. The original on and off, if this bit's on, this new bit's on. But if this new bit's off, you could have that on or off also. So you double your options. So now you have these 4 options if this third bit is on, and you have 4 options if the third bit is off also. So you have these 4 plus these 4, which is 8. Then you have 8 if this 4th bit's on, and 8 more if this 4th bit's off. So you have 16. If you notice, it doubles each bit that you add, because you have the same amount of options you did before if this was on, and you have that same amount added to it. In other words, double the original amount if this is off. So you can say in computing, 8 bits is a byte, and you've heard of megabytes and megabits. So 8 bits is a byte. And if you say, okay, so it's 2 options with 1 bit, that times 2 with 2 bits, so it's 2, 4. That times 2, so 4 times 2 is 8. That's 3 bits. Double that 16. Double that's 32. Double that's 64. Then 258, or 64, and 128, then 256. So with 8 bits, you have 256 different options. And if you notice, the levels of brightness for each of those LEDs ranges from 0 to 255. So ranges from 0 to 255, and that's 256 bits. So that's yeah, how those things work. And so that's how those things work. So if you have each of those, if there's 8 million LEDs, if there's 8 million pixels, and if there's 8 million pixels with 3 lights inside of each pixel, that's 24 million lights inside of 4K television in general. It's approximately like that. There may be some variations and stuff, but just rough estimate. So you have all that stuff. Then you can say, just think of on your screen, there's one picture, and then it has all these things, these pixels adjusted to, make up an image. Because if you zoom in really close, if somebody zooms in really close to a TV or whatever, you could see little dots, and each of those has a red, green, blue light in it. If it's done certain ways, you could actually, with a magnifying glass or whatever, probably, or I guess a person could see the individual LEDs in each pixel. So that makes up one picture. And then if you remember the old flip books that like how people used to draw cartoons, and they would flip through them really fast, and you see it go, and it would look like pictures that were turning into motion. And that's because we had a picture like something like this, and then the next picture might be slightly over here, and the next one here, and here, and here, and you combine it, and it would look like this. Be over here, then here, then here, then here. If you combine them, it would look like this, kind of. And so it would look kind of like motion. And if you do that fast enough, then the brain thinks there is motion, and then you have videos like this, or videos in general. And if you heard of FPS, or frames per second, or refresh rate, or hertz, Hertz, within a computer monitor or television, then that's what it's talking about, is how many frames per second are showing up. And so if it didn't make these certain efficiency adjustments in the background that I'll mention in a little bit, then it would be computing, like for 4K, it would be 8 million. For 4K, it would be the 8 million pixels with 3 LEDs in each pixel, with 3 lights in each pixel, so 24 million lights. And if a refresh rate is, just say, 60 frames per second, then that would be 24 million things 60 times a second that it would be calculating or showing up. And that would come out to be a large number. So 24 million times 60 is roughly 1.5 billion things per second. So that's a bunch. But there's some things that it does in the background that makes it work better and way more efficient. Because I think, like, if you look here, see, I'm moving, but my background is not moving. So I think the way it packages data is it's keeping a lot of the same pixels and stuff in the background color in the same position, so it doesn't have to recalculate them. And as I'm moving, instead of it recalculating everything over and over, I think it's mainly moving the pixel values over. Like for right here, from where the skin goes to the shirt, if I screwed over like this, there's still skin goes to the shirt, it's just shifted over. So it shifts it over so it doesn't have to recalculate part of that. And I think from what I've observed, I'm not 100% sure this is correct, but because I haven't looked up to verify it, but from what I've observed is when there's a bunch of background and stuff changing at the same time, if there's a slow computer, if there's the foreground and the background changing a lot, then if there's new stuff and if there's newer stuff and all that going into the image or the video, then I've noticed if it's a high quality video and low quality computer or whatever, then it starts kind of freezing up. And I think that's probably why. So you might look that up and let me know in the comments if you verify that's correct. That part is just from my observation. I haven't checked it to verify it. So yeah. And most useful thing I think is at least from my perspective, is receiving God's love. Somebody went to Jesus, said, "What's the most important commandment?" He said, "Love God with all your heart, soul, strength, and mind, and love your neighbor as yourself." So love everyone, and like he even said, love your enemies, and so love everyone. And the only way we can is receiving this love first, because if somebody came up to you and said, "Hey, give me $1 million," you'd be like, "Hey, I don't have it," probably. But if somebody came up to you and handed you $100 million and said, "Hey, give me $1 million," you'd probably be like, "Okay, you just handed me $100 million. Here's $1 million." And so the only way to give was because you had to receive first, and the only way we can give is because we had to receive first. So that's like giving. From my perspective, it's like giving God's love. The only way we can is receiving it first into different areas of life and stuff like that. And so, and it's it's a process or whatever too. But in my view, when we ask Jesus in our life, it's like connecting the light switch to His infinite love, and then it can flow through us. It's like He comes and lives inside our house, even though the house, it may still need rearranging and remodeling and so on. It's a process, but He's in there, and it's the light's on. And so yeah, so anyway, those are my views on some stuff, and let me know your views about any of this in the comments, because I love looking from different viewpoints. Yeah, it's just, I like science and knowledge and stuff. And so I've studied probably 15,000 or more hours in the past 15 years, and I really like knowledge. What I really like is finding common patterns among seemingly unrelated things, and that's pretty cool. How like a common thread woven among the different seemingly unrelated subjects, and it's just pretty interesting to me. So let me know what you think in the comments, and thanks for listening. And so bye. Love you all. Have fun. Bye. Thanks for watching. Please click like and subscribe.